Ever wondered how your data stays private during complex computations? Let's dive into the world of secure computation technologies. These technologies are super important, especially in today's digital age, where our personal information is constantly being shared and analyzed. I mean, think about it. Your medical records, financial data, even your online activity, it's all out there. That's why we need robust ways to protect our data while still allowing for valuable computations. Over the next few chapters, we're going to explore some of the most exciting and promising technologies in this space. First up is Secure Multi-Party Computation, or MPC. Imagine you and your friends want to calculate your average salary without anyone revealing their individual income. That's essentially what MPC allows. It's a cryptographic technique that lets multiple parties collaboratively compute a function over their private inputs without actually revealing those inputs to each other. How does it work? Well, it involves something called secret sharing. Each party splits their private data into multiple shares and distributes them among the other participants. No single party has all the shares, so no one can reconstruct the original data on their own. Then, the parties perform computations on these shares in a way that the final result can be combined and revealed. But the underlying individual inputs remain secret. A great example of MPC in action is Partisia blockchain. They're using MPC for privacy-preserving data sharing and analysis. Essentially, this allows them to run complex computations on sensitive data without compromising individual privacy. It's like having your cake and eating it too. Next, we have fully homomorphic encryption, or FHE. This one's a bit of a mouthful, but it's a really cool concept. Imagine being able to perform computations on encrypted data without ever decrypting it. That's the power of FHE. It's a special type of encryption that allows for computations to be performed directly on ciphertext, producing an encrypted result which, when decrypted, matches the result of operations performed on the plaintext. Here's how it works. You take your data, encrypt it, and then send it to a server. The server can then perform computations on this encrypted data without ever seeing the actual data itself. The results are then sent back to you, still encrypted, and you can decrypt them to get the final output. It's like magic, but it's actually some really clever cryptography. Now, FHE is still computationally demanding, which means it takes a lot of processing power. But major tech companies like IBM, Google, and Microsoft are investing heavily in its development, and we're seeing some promising advancements that could make it more practical in the near future. Now let's talk about zero-knowledge proofs, or ZKPs. ZKPs are like a magic trick. They allow you to prove that you know something without revealing what that something actually is. It's like saying, I can prove I have the key to this door without showing you the key itself. There are different types of ZKPs like ZK snarks, zero-knowledge succinct, non-interactive arguments of knowledge. These are particularly efficient and have gained popularity in various applications. One of the key areas where ZKPs are making waves is in blockchain technology. For example, they can be used to verify transactions without revealing the sender, receiver, or amount transacted. This allows for greater privacy and security on the blockchain. Beyond blockchain, ZKPs have applications in authentication systems, anonymous voting, and even proving the integrity of computations without revealing the underlying data. Moving on, we have Trusted Execution Environments, or TEEs. Imagine a secure enclave within your device where sensitive data and computations can be isolated and protected from prying eyes. That's essentially what a TEE provides. It's a secure area within the main processor that's designed to protect code and data in use from software running at a higher privilege level, such as the operating system. There are a few examples of TEEs out there. Intel has SGX, and ARM has TrustZone. These technologies create a hardware-based security boundary within the processor, ensuring that code and data running inside the TEE are protected from external access. Of course, no system is perfect. While TEEs offer a strong security model, they are not immune to vulnerabilities. Researchers have identified potential attacks that could compromise the integrity of TEEs. However, ongoing research and development are constantly improving their security. TEEs are finding use in various applications, including secure payment processing, biometric authentication, and secure key management. Platforms like Secret Network are leveraging TEEs to enable privacy-preserving smart contracts, opening up new possibilities for secure and confidential computations on the blockchain. Last but not least, let's talk about differential privacy, or DP. DP is a bit different from the other technologies we've discussed. It's not about keeping data completely secret, but rather about adding noise to datasets in a way that protects individual privacy while still allowing for statistically meaningful analysis. Imagine you want to conduct a survey about sensitive topics, but you want to ensure that individual responses cannot be traced back to specific participants. DP can help with that. It works by adding carefully calibrated noise to the data, making it difficult to infer individual responses while still preserving the overall statistical properties of the dataset. There are two main mechanisms used in DP: noise addition and query restriction. Noise addition involves adding random noise to the data, while query restriction limits the number and types of queries that can be performed on the dataset. While other technologies like MPC and FHE focus on keeping data completely confidential during computations, DP takes a different approach. It acknowledges that some information leakage is inevitable, but it aims to minimize and control that leakage to protect individual privacy. DP is often used in conjunction with other privacy-enhancing technologies to provide a layered approach to data protection. So there you have it, a quick tour of some of the most exciting secure computation technologies out there. From MPC to FHE, ZKP to T, and finally DP, each of these technologies plays a crucial role in safeguarding our data privacy in the digital age. Whether it's ensuring secure computations on sensitive information, enabling privacy-preserving transactions, or protecting individual privacy in large datasets, these technologies offer powerful tools for enhancing data security and confidentiality. If you're interested in diving deeper into any of these technologies, there are tons of resources available online. You can check out research papers, blog posts, and even open-source projects that are pushing the boundaries of secure computation. The world of data privacy is constantly evolving, and it's up to us to stay informed and advocate for our own privacy rights. Remember, your data is valuable, and protecting it is essential. So stay curious, stay informed, and protect your data privacy.